Lesson 5.1 is on graphing reciprocal functions. You want to recall that the parent reciprocal function f of x equals 1 over x, and f of x is then called the reciprocal of the original function g of x equals x. So in actual fact, f of x and g of x are called a pair of reciprocal functions since f of x equals 1 over g of x. So I have a very simple example here that we started with, and that is a parent function here, which is in blue, which is g of x equals x. And you look at the characteristics of this function, which is in blue, and the reciprocal function, which is f of x equals 1 over x, which is in red. So let's just look at them a little closely. For g of x, you can see that the zeros, or the x-intercept, is this number 0. There's only one 0. And we can see that the g of x is greater than 0 for values of x from 0 to infinity. So all these values of g of x are above 0, so they're positive. Whereas from negative infinity to 0, which is this half of it, is less than 0. And the intervals of increase, that is, if you go from left to right, you can see that this function is increasing from negative infinity to positive infinity. And there is no intervals of decrease, okay? Now let's look at the characteristics of the reciprocal function f of x. You notice that there is a vertical asymptote at the y-axis, which has the equation x equals 0. And the function is positive at all values of x that are greater than 0, so from 0 to infinity, and negative for all values of x from negative infinity to 0. So you can notice here by comparison, f of x and g of x are positive or above 0 in the same intervals, and they're also below 0 or negative in the same intervals. Now looking at the red graph for the intervals of decrease, you can see that as you go from left to right, the function is decreasing from 0 to infinity, and it is also decreasing from 0 to positive infinity. So you could say the intervals, there is no interval of increase, but there's only intervals of decrease. And some people might say it's decreasing from negative infinity to positive infinity, but actually there is a break here at x equals 0. So another way of writing this would be it's decreasing from negative infinity to 0, and then from 0 to positive infinity, stating that there is a break that's happening at 0. So the intervals of increase and decrease are kind of opposite. So if the original function g of x is increasing, and that same interval, the reciprocal function at 1 over x is decreasing. There's two interesting points here, which I want to point out to you. One is this point here and this point here. They are there on both the reciprocal functions. Okay, so they're kind of the points where they intersect, and they're called non-variant points because they are there on both of them. So for this particular example, the coordinates are 1, 1 and -1, -1. And so to find these points, you can always find them at the y values of 1 and the y value of -1. So if you put the y value of 1 into a given function, you can find one of the non-variant points. And if you put y value as -1, also you can find the other invariant point or non-variant point. So let's look at some examples of reciprocal linear functions. The one we just now saw, I'm going to repeat that again here, which is y equals x and y equals 1 over x. I did a table of values for both of them. As you can see, these are the table of values for y equals x. This is the table of values for the reciprocal function. The 0 is at 0, 0 for the y equals x function. And you can notice that where you have that 0, that becomes the vertical asymptote of the reciprocal function. So the 0 was right here. So if I were just to highlight that, this is the 0, and that particular vertical line that passes through it becomes the vertical asymptote of the reciprocal function. And there is also a horizontal asymptote, HA, which I write for short, which is the x-axis, which has the equation y equals 0. The line that I have plotted here is the given function y equals x. And if I wanted to plot now the reciprocal function, I have to first highlight the the asymptotes. I'm just going to put that in pink here. This is the the vertical asymptote x equals 0, and this is the horizontal asymptote y equals 0. So when I want to graph now the reciprocal function, I'm going to take these points and I'm going to find that they're going to look something like this. They're going to approach the asymptotes on both sides like this. Okay, so while I'm doing this, I want you to pause the video and I want you to take out graph paper and actually try this, because as you plot them, you will kind of understand it better than just watching me in this video. So I want you to pause, and for each example, I want you to try them on your graph paper also as I'm doing these examples with you. Let's take another example, which is the original function is f of x equals 2x plus 3, and its reciprocal function g of x is 1 over 2x plus 3. So I kind of made a table of values for the original function. And I noticed that it has a 0 or an x-intercept at negative 1.5. And so I know now that that's going to become my in the reciprocal function, I'm going to notice that it's at that same point that I'm going to have a vertical asymptote. Because when I do 1 over 0 for the reciprocal, I'm going to get undefined, right? So that's going to be where the vertical asymptote is. So I graphed here on graph paper the line f of x equals 2x plus 3. Now, if I want to graph the reciprocal function, I know that the vertical asymptote happens at negative 1.5, which is right here. And I'm going to take my ruler, which you should do when you're doing this, and draw a vertical asymptote right there and immediately write its equation, x equals negative 1.5. There's also a horizontal asymptote, which is the x-axis, which has the equation y equals 0. I'm going to plot that and write the equation right away next to it, which is y equals 0. And now I can plot, without even looking at these points, I can plot the reciprocal function. So my idea is to look for the invariant points. The invariant points will be where y is equal to 1 and y is equal to negative 1. So y is equal to 1, the point the original function is there, and the negative 1 is right there. So I know that in my reciprocal function, they're going to pass through these points and they're going to approach the asymptotes. So let me use a different color here. It's going to have to pass through that invariant point and approach the horizontal and vertical asymptote that way. Similarly, on this side, it's going to pass through the invariant point and go this way. So this green is the function g of x. Okay, and you can also see, like, the original function is increasing, right? It's increasing from negative 1.5 to infinity, and that same interval, your g of x is decreasing. And in this interval, it's also increasing and it's decreasing in the reciprocal. So the opposite behavior. And they are positive in the same interval. So it's all positive over here from values of x that are greater than negative 1.5, and the same behavior for the line. And you notice that it's negative for values of x less than negative 1.5 for both g of x and f of x. So those are some observations that you must make. So when you're graphing a function and it's reciprocal, please highlight as soon as you figure out the asymptotes, write down their equations beside them, and then plot the points after locating the invariant points. So what are some key concepts? The reciprocals of quadratic functions with two zeros have three parts, with the middle part reaching a maximum or a minimum point. This point is equidistant from the two vertical asymptotes. The behavior near asymptotes is similar to that of reciprocal linear functions. So we haven't looked at reciprocal functions yet. We've only looked at reciprocals of linear functions. We're going to look at reciprocals of quadratic functions next. So they're going to have three parts. So something like this, when you plot it, you're going to find that, instead of just having one part, like we saw, we might have maybe, we could have two vertical asymptotes, and then when you're graphing this, you might find that one of your one part is right here of your reciprocal function, another part is here, and a third part is up here. So that's what they meant by having three parts. Okay, and then you would find that the middle part could have a maximum or a minimum, like you notice over here, and it's equidistant from both the two vertical asymptotes. So let's take an example to understand that better. So we have here a quadratic, a reciprocal of a quadratic function, 1 over 2x squared minus 9x minus 5. If we wanted to now find the zeros or the x-intercepts, we can put the function as equal to 0 because the 0 means the value of x when y is 0. So set y is equal to 0 or f of x equal to 0. And if you do that, you will find that this becomes 0 equals 1 over this, 0 equals 1, which makes no sense. So therefore, there is no x-intercepts for the reciprocal of this quadratic function. So for a rational function, only the numerator determines the x-intercepts. Here we can see that when we set this is equal to 0, you get 0 equals 1 over 2x squared minus 9x minus 5. And you will, if you say you cross multiply, you'd get 0 equals 1, which doesn't make sense. So there's no x-intercepts. Okay. Let's try to find the y-intercepts. To find the y-intercepts, you put x equals 0 in the given function, and you'll find it works out to negative 1 over 5. So the y-intercept is having the coordinates 0, comma, negative 1 over 5. The vertical asymptotes, we can set the denominator to 0 and solve for x. Okay, so the denominator is, for the function that's given to us, it's f of x equals 1 over 2x squared minus 9x minus 5. We're going to set the denominator as equal to 0. So we're going to set 2x squared minus 9x minus 5 as equal to 0. And we're going to solve for x. We can factor this as 2x plus 1 times x minus 5. And then we find that x equals negative 1 half or x equals 5. So because these are in the original function, so let's call the original function g of x, let's say. The original function would have been 2x squared minus 9x minus 5. It would have been a quadratic function. And the zeros of this quadratic function would have been what you got here, which is negative 1 half and 5. And so those will become the vertical asymptotes in the reciprocal function. Okay? So that's what we're going to do is once we find that when we set the denominator is equal to 0 and we find the two zeros, that means the vertical asymptotes are x equals negative 1 half and x equals 5. Those are the equations of the vertical asymptotes for this reciprocal function. So we have found out the vertical asymptotes, there's two of them. The horizontal asymptote is going to be the x-axis, which has the equation y equals 0. And that is true for all rational functions where the degree of the numerator is less than the degree of the denominator. Okay, so over here, the degree of the numerator is 0, the degree of the denominator is 2, so it is less. The degree of the numerator is less than the degree of the denominator. So by default, for those kinds of functions, you'll always have the horizontal axis as, or horizontal asymptote as the x-axis, which has the equation y equals 0. So I'm just going to do this in a different color here so you can see that. This is the horizontal asymptote. We have two vertical asymptotes, one at x equals negative 1 half and one at x equals 5. So that would be negative 1 half would be somewhere here. 1, 2, 3, 4, 5 would be here. So you have two vertical asymptotes like that. And you want to write their equations also next to them. So that's x equals negative 1.5, x equals 5. All right, you have your two vertical asymptotes. And then you're going to try to graph the function of the reciprocal function. So what we're going to see is we're going to find that the function is going to be something. It's going to be something like this, and over here it's going to have this shape, and over here it's going to be like this. We could also get more closer points if we found let's say we graphed the original function, which is y equals, let's say g of x equals 2x minus 1 and x minus 5. Or what would that function look like? Let's try to draw that. So its zeros would be negative 1.5 and 5, and it would have a y-intercept of negative 5. So 1, 2, 3, 4, 1, 2, 3, 4, 5, and it would be, so how does it actually look for this function? If we were to graph the original function, 2x squared minus 9x minus 5, it opens up and has a y-intercept of negative 5. One, two, three, four, 5.